cover in section 2.1? Quadratics. And quadratics are a degree of 2 because the highest x power is 2, right? So then when we're in section 2.2, polynomial functions of higher degree, that means we could have x cubed, cubic graph, x to the 4th, quartic graph, etc., etc. They can get messy. But first of all, really quickly, characteristics of polynomials. They are always continuous. One description of continuous, you don't learn until calculus the definition because you don't know what it all means yet. But continuous, one way of saying it, no breaks, no holes, no gaps. Another way of saying it is you can draw the graph without picking up your pencil. That's a silly way of saying it, but it's technically somewhat mostly true. Meaning, is this continuous? No. Why? Because I had to pick up mine. Yeah, I had to pick up my pencil. That's not continuous, right? The one tricky one with that is this. You can technically not pick up your pencil and still draw it. But if you're actually indicating the values, oh. So anyway, that's the one exception to this little silly rule. Piecewise functions can be discontinuous. Piecewise functions can be discontinuous, but most other functions, besides those with holes or vertical asymptotes, and especially all polynomials, are never going to have any jumps or breaks. Second characteristic, smooth turns. What does that mean? You're always going to have curved turns whenever it turns or changes direction from increasing to decreasing, etc. They're going to be smooth. What's an example of a sharp turn? An absolute value. But is he a polynomial? No. Why? I can't rewrite absolute value as a power. And not as a whole power at that. Our goal for the entire section is can we graph now see bigger polynomials by hand. It's intimidating, but I think we can. Here we go, basic function for monomials. The basic function for monomials, just x to the n. There's no extra terms involved. No extra terms involved. N has to be greater than 0. If n is even. Examples. X squared, x to the 4th, x to the 6th, etc. If n is odd, x, technically 1, x cubed, x to the 5th, etc. If I was to have you get out your graphing calculators and put in x squared and put in x to the 4th and put in x to the 6th, do you guys know what's going to change?
It does the many times that it does the little wave.
Actually, no waves if it's just a monomial. It has to have plus extra terms to make it all bumpy in between. X to the 4th is going to look super, super similar, but everything is increasing faster and decreasing faster. And x to the 6th, same thing. Everything is increasing faster and decreasing faster. Why? Because it's raised to the 6th power and not the squared power, to the 4th power, not the squared power. So if we plugged in, for instance, 2 squared is only 4. It only goes up so high. 2 to the 4th, though, man, that's 4 and 4. That's 16. Oh, my goodness. And 2 to the 6th, oh, that's 8 times 8, which is 64. It's way up there. So the higher the powers get, the steeper the graph gets. However, what do you notice about as you go to the right and as you go to the left of every single even-powered monomial? They're both going up. And if there's a negative in front, what are they both doing? They're both going down. Odd ones. We could have y equals x. We could have, now y equals x is funny because he's a line. But we have y equals x, then roughly, technically that line should be a little bit more up probably. Then we have y equals x cubed. And then guess what's going to happen with y equals x to the 5th? What's it doing? Decreasing? Well, technically it's increasing if we go left to right. Increasing quicker and increasing quicker. Once again, 2 cubed is 8, but 2 to the 5th power, well, that's going to be 8 times 4 is 32. It's a lot steeper, we'd say. But still, what do you notice about as you go to the left, what are all the graphs doing? Decreasing. As you go to the right, they're all increasing. Okay. Leading coefficient test. Leading coefficient test. That just means, hey, leading coefficient, we know that. It's the coefficient of the highest degree term, right? For a quadratic, it was the x squared term. For a cubic, it'd be the coefficient of the cube term, etc. We look at the coefficient of the leading term, and we're trying to ask ourselves, what's going on at the ends? And by the ends, I mean 2 the right, and I mean 2 the left. End behavior, I mean as you go to the ends, to the right towards positive infinity, and to the left towards negative infinity. We already kind of know what's going to go on though, I think. If n is even, we can use an example. If n is even, if we were to use like x squared, but it could also be x to the 4th and x to the 6th, etc. However steep it is, every even function, as you go to the right and go to the left, if a is positive, it's going up. However you connect it, whether it's like a wide parabola, whether it's a skinny parabola, however you connect it, to the right, we would say, the y's are going up, the function is increasing, and to the left, the function is increasing as well. Now there are snazzy ways of saying this. And the snazzy way of saying it is as x approaches infinity, f of x approaches infinity. I'm going to go ahead and translate that phrase. To the right, f of x, or I could say the y values, or the function approaches infinity. As x approaches infinity, f of x approaches infinity. What's another way of saying it? As I go to the right, the function is increasing or going up. So similarly, I could also say as x goes to the, how could I show going to the left? To the right is x approaching positive infinity. To the left, x approaches negative infinity. What are the function or y values approaching? Where is it going as I push to the left? No, as I push to the left, as I go to the left, I'm reading backwards. Where's the function going? To infinity. You see it? Isn't it going up to the left and up to the right? We're just writing it in really snazzy math terms. Now what if a is negative? Doesn't matter if it's a somewhat wide parabola or a super steep parabola, whatever the even powers are. If a is negative, how would you guys finish the statement as x approaches positive infinity, f of x approaches? Yeah, as you push to the right, where's the function going? Down. Do you see how the little arrow just means it's going down, it's approaching down, it's headed down? Does that make sense? And so what if I was to say as x approaches negative infinity? You're reading backwards now. Where's the function going? As I go left, it's also going down. So we're seeing kind of basic statements, but we're seeing them with really snazzy notation. Now what's going on with odd functions? If a is positive, it's going to have that normal member parent function, that normal cubic parent function type graph. Whether it's steep or whether it's wide. Just setting it up. The top one, as x approaches where? Positive infinity. Can you give me a simple way of thinking about it? To the right. As I head to the right, as x approaches positive infinity, where is f of x going? Up. But how would I answer this statement as x approaches negative infinity, or as I read backwards to the left? Goes down. Negative infinity. So what's going to happen if the leading coefficient is negative? If this is the normal way, what happens if I now have negative on the outside? It's kind of reversed, but I wouldn't go that way. I would go this way, right? It's a vertical flip if it's on the outside. But does it still end up being the same thing? Okay, yeah. Whether it's steep or whether it's not so steep, all I'm going to say, everything flips. Now, still push it to the right, so this x stays the same, but what happens to the y's as I push to the right?
They get negative.
Yeah, they go to negative infinity. And what happens to the y's as I push to the left? Or head to the left?
They approach infinity.
They go up. Okay, snazzy rotation. For pushing to the right or pushing to the left, and whether it goes up or whether it goes down. Okay? Now hold on. We're able to tell all of this information from what? Well, the graph, but come back. Couldn't we look at an equation, and couldn't we look at the leading coefficient, and technically with however many terms it has, and couldn't we answer the question, what's going on as I head to the right or head to the left? From this page. Now, here's the snazzy notation again. But what's going on with these graphs? Are they as nice and simple as these ones? No. They're starting to get a little loop-de-loop in between. And here's the head, or the main idea. How do you get loop-de-loops in between? You don't just have
When A is has a
an
number.
x 1, 2, 3, 4, 5. You don't just have an x to the 5th power, you also have an x to the 4th power, and 3rd power, and squared power, and number, and a constant that messes everything up. It doesn't mess it up, it definitely distorts it. You don't just have an x 1, 2, 3, an x cubed, you have some in-between terms that mess it up. But do you guys notice that even if the cubic gets messed up, if the leading coefficient is positive, doesn't it end up to the right going up and to the left going down, just like we had over here? So it doesn't even matter what funniness happens in between, the end behaviors will remain the same. Does that kind of make sense? No matter how messy they get, the end behaviors, no matter how messy even evens get, as long as the leading coefficient is positive, you're going up to the right, up to the left, and down to the left, down to the right, the leading coefficient is negative. So, we're going to end-ish here today. But the sad thing is we definitely have more to do. I was hoping we could finish it, but that worksheet was just a little too long. Section 2.2 will be due on Monday. But if I were you, I would try to get as ahead in other classes or as caught up in other classes as you can tonight. But wait, look, what's the dilemma? What should you work on tonight for my class? Don't work on this. Just a heads up, you need to do a lot more tomorrow. Work on this. Sound good? Oh, wait, hold on. Guys, we still have a minute and a half. Look at these messy equations. Look at these messy equations. I just want you to answer the question for each and every one of them. As x approaches infinity, and as x approaches negative infinity, and I want you to answer the question, what will f of x do? Okay, for the first one, as x approaches infinity, tell me what that means. As you move to the right, what's going to happen with an odd function with a negative? Pause. Visualize. Because some of us are like, what's a cubic look like normally? Right? What happens if no? There's a negative. Okay, as you go to the right.
Oh, pal, Lauren Carroll. Here are the results for the homecoming court princesses. The freshman princess is Peyton Northrop. The sophomore princess is Catherine Arvizu.
Yeah!
The junior princess is Emily Zipperman. And your homecoming court for 2016, Isabella Abdallah, Nikki Hustero, Gracie Jensen, Arabella Ramsey, and Kara Zipperman. Congratulations, ladies.
Of course, Nikki is amazing again.
Thank you.
There's only 6 votes? Yeah. Huh. Zipperman. Pause. We're still 5 seconds. If it flips, does it make sense to the right down and to the left up? Whatever is going on in between. Alright, cool kids, we'll come back tomorrow. These polynomials get funny. Please work on corrections and then we can focus.
Yes.
Happy nutrition. Hi guys. Got it all?
So,